Here we have the infinite series of 1 divided by e to the n squared, and we want to show that this infinite series converges by using the direct comparison test. And once again, to use the direct comparison test, we will call this right here a sub n, and then we need to come up with a b sub n. And then since we're trying to show that this infinite series converges, then we need to come up with a b sub n such that this series is less than or equal to the series b sub n, and also that the series b sub n converges. And so we have to do two things. First, we need to come up with b sub n, and then show that we have to show two things: that the series a sub n is less than b sub n, and the series b sub n converges. And so what we do is let a sub n be the given sequence here. So and then come up with something similar or something that we know something about. So let for this one, for this particular one, let's go ahead and use 1 over 2 to the n. And we want to use this because we know that e again, e is 2.71828 approximately. So this is e to the n squared. This is greater than 2 to the n. And then if we do the reciprocal, 1 over e to the n squared will be less than 1 over 2 to the n. And notice here that this is the same as this. 1 over 2 to the n. And so we have come up with a b sub n. Now we have to show two things. We have to show that the series a sub n is less than the series b sub n. And we also need to show that the series b sub n converges. So we have to show two things. And so we have this series right here. Is less than the series 1 over 2 to the n. Because 1 over e to the n squared is less than 1 over 2 to the n. So we have shown the first part. And now we need to show that b sub n, which is this right here, converges. And then we can rewrite this as the 1/2. And notice that this is a geometric series. With common ratio. R equal to 1/2. And recorded for geometric series, if the common ratio is between -1 and 1, then the series converges. So it converges by the geometric series test. And so we have shown two things. And again, when the series converges, what we're saying is that this series right here is equal to some real finite number. And for example, like if we let the number be like k or something. And so that's what it means for a series to converge. That this infinite series right here is equal to a real finite number. And so this series is a positive series, meaning this series is consisting of positive terms only. And therefore this is what we have. So this is 0, got to be like 0, and then this is equal to some real finite number. And so that means this thing right here is bounded between 0 and some real finite number, and therefore it converges also. And that's the logic behind the direct comparison test. Is that we're trying to show that this series right here is bounded above by some real finite number, and therefore it must converge. And so once again, to use the direct comparison test, we have to come up with a series B sub n. And if we want to show that the series A sub n converges, then we have to show that the series A sub n is less than the series B sub n, and that B sub n converges.